In this video, I want to look at generators of arbitrary cyclic subgroups of order n. So basically, we're going to be writing G is equal to the cyclic group generated by little g, where G to the n is known to be E. And we could do this from scratch, but it turns out that there's an easier way. I want to remind you that we already know something. We know that a cyclic group of order n is isomorphic to Zn. It's just a matter of dealing with the times in G versus the plus in Zn. And I know how the isomorphism works. The isomorphism is given by G to the k inside group G corresponds to k inside Z sub n. So what this tells me is that G to the k, and let me clean up my handwriting there, G to the k is going to generate all of G if and only if k generates all of Zn. But I know from the previous video that k as a generator in Zn happens if and only if the GCD of n and k is equal to 1. So what I know is this fact. If G is a cyclic group of order n, then G to the k is a generator, so the cyclic subgroup generated by G to the k is the whole group, if and only if the GCD of n and k turns out to be 1. The other fact that we know about orders inside Zn also generalizes. So I can also say that if I look at GL inside of the cyclic group generated by G, then the order of GL is going to be nothing more than n divided by the GCD of L and n. And this is because G to the L is going to correspond to L over n, my Zn group. And I know that the order of L is equal to n divided by the GCD of L and n from the previous video. It is worth noting that if I look at G to the 0, that is equal to E, and the order of G to the 0 will be the order of E, and that will be 1 since E to the first is equal to E. Or if you wanted to, you could say G to the 0 raised to the 1 is equal to E. So the order of G to the 0 is equal to 1. So orders in all cyclic groups work exactly the same way they do inside Zn.